Now let's talk about interpreting kurtosis. Oh, I actually said that I would talk a little bit about where the skewness stuff goes. Let me just draw it over in this corner. So I'm not going to need all this room for kurtosis. So let me just talk a little bit more about the skewness function here. The formula for skewness, as I said before, is going to be the sum of all the cubed distances over, some constant and s cubed, right? I said that that's the idea. Now, sometimes you might see this formula written more like this, with x sub I minus the mean cubed over s to the third power. Now, this and this, they really mean the same thing. It's just different ways of writing it. This actually only affects things that are affected by this I. And because this is not affected by the I at all, I mean, s cubed will be the same whether it's for the first value or the last value. It doesn't actually matter whether you write it inside, included in that big sigma or not. Another way you could write it is also 1 over s cubed times x sub I minus x bar cubed, right? So this is yet another way you could write it. And so all of the three ways of writing it are equivalent. It doesn't change anything. And so don't get tripped up if you see one of these other options. They're not trying to be tricky. All right. Now let's talk about kurtosis. So kurtosis as a concept is sort of weird for people because this is not something that we're used to dealing with in regular shapes. Like we know roundness and we know like squareness, but kurtosis is something a little bit different. Kurtosis is really about two things sort of bundled into one. One is pointiness, right? Peakedness. So very kurtotic shapes might look something like that. Super non-kurtotic shapes look something like that. So one important aspect of this is the pointiness, right? Peakedness. But at the same time that peakedness is going up, what you're seeing is the tails becoming thinner, right? So peakedness and thin tails usually go together. And kurtosis is about both of those things because here we not only have no peakedness, but we also have fat tails. The tails are just as fat as that lack of peak in the middle, right? And so something in the middle might look something more like that, right? So this is a kurtotic sort of dimension where you're getting increasing kurtosis. And when you have increasing kurtosis, it means two things simultaneously, having more peaks, but also having thinner tails. All right. So now let's talk about calculating kurtosis. So kurtosis, let's talk about the main heart of the idea before we get into things. Like skew, you could multiply constants to it. It sort of doesn't matter. This is the heart of kurtosis. Here's my sigma. It's going to be that same distance for each point away from my mean. But instead of cubing it, we're going to raise it to the fourth power. Now, when we raise it to the fourth power, we know that we do not care about whether it is on the left side or the right side, right? So that's one thing to note already about kurtosis. It's not counting how many are on one side versus the other side of the mean. So kurtosis already, we know it'll probably be positive because it's going to raise everything to the fourth power, and when you raise something to an even numbered power, it's going to be positive. And then we're going to divide that by s to the fourth power, standard deviation to the fourth power. Now, once again, this is going to always be positive. Standard deviation is already positive, and then we're going to raise it to the fourth power. So kurtosis is largely going to be a positive number. The only difference between different values of kurtosis might be whatever constant they decide to multiply by. Frequently, n minus 1 over n minus 1 is one of the constants. I forget what Excel does. Excel does something else crazy. We'll figure that out when we get there. But once again, even with kurtosis, you could write it in a number of different ways. You could write it as 1 over n minus 1 times s to the fourth power, and then put your sum of fourth powers here. Sum of quads? I'm not really sure. Right? So instead of sum of squares, we're raising it up to the squared squares, right? So that's one way of writing it. Another way of writing it is you can make the sigma sign really big, x sub I minus the mean to the fourth power over n minus 1 times s to the fourth power, right? But all of these things are the same thing. And once again, this is really the heart of the idea of kurtosis. And one of the reasons it's to the fourth power is, let's think about it. Remember, it's very concerned about being either on the outside or on the inside of the distribution. Are you on the tails or are you at that peak? And by raising it to the fourth power, it makes everybody matter a lot. And especially if you're on the outside, you matter way more than if you're on sort of the inside. All right. One more thing to the idea of kurtosis. Now, typically, kurtosis is going to be, so for a normally distributed function, let me draw it here. For an approximately normal-looking distribution, nice bell curve, right? The kurtosis, if you calculate it with some function like this, is going to be 3, right? And that's so arbitrary, right? Just this weird number. And so what they've done is they've made the kurtosis function so that you subtract 3 from it, so that the normal distribution has a kurtosis of 0, right? Because 3 minus 3 is 0. And so that's how you actually get negative kurtosis. It's not because of this function, but it's because you subtract by 3. So the lowest kurtosis you could get is negative 3. So that's sort of this odd, bizarro thing. I'm not really sure why they decided to normalize it to 0, but my theory is that they thought it would be hard for people to remember, like, above 3 is like something from normal and below 3 is something from normal. So they just make you do it in the formula. All right. So now that we have this like weird correction of subtracting 3, now we could talk about interpreting kurtosis. You already know that a kurtosis of about 0 would mean that you have an approximately normal distribution. Oops, it's a crappy normal distribution there. All right, so that's what a kurtosis of 0 would be. A kurtosis of less than 0, and a kurtosis that's greater than 0 is going to be more peaked, more pointy than normal, right? So something like this, right? So that's a kurtosis that's greater than 0. And we call that leptokurtic. It just means more peaked than normal. Now, we could call other things that have a kurtosis that are similar to the normal distribution. We could just say they are similarly kurtotic to the normal distribution, but that would be really long. So we say they are mesokurtic, because you don't have to be a normal distribution to have a kurtosis of 0. Mesokurtic just means it's about the same peakness as normal. Right? So that's mesokurtic. Because we can't leave well enough alone. We need to have another for something that's less peaked or like flatter than normal. And I like to remember this because, you know, mesokurtic, leptokurtic, that always sounds crazy, but meso, I just remember, oh, it's like in the middle, so middle kurtosis. But lepto is hard for me to remember which it is. But that's why this last one helps me, because this one I could always remember. It's called platykurtic, and I think of a platypus and how it has like a flat beak. So platykurtic, that means this is flatter than normal, so smaller peakness. Than normal. Right? So that would be something that looks more like this. Right? So that's platykurtic right there. So those are our 3 interpretations of kurtosis. Now let's go to our Excel examples and look at kurtosis there.